just bear with me for a sec. Cool. Okay, I'm going to shut this off because I don't need it. All right, so linear algebra is a very, it's a very broad topic, right? Like, who here knows what linear algebra is, like in general? So what do you think it is?
Algebra that's linear.
It's about as good of an answer as I think you can give. Yeah, it's not a very easy to define course. Maybe right now what you're thinking is like, oh, it's like solving linear systems of equations, and like to an extent that's right, but that's not the full extent of it, right? Like a lot of you. Another thing that a lot of students think is like it's the math behind matrices, because that's kind of what it feels like, right? It's like doing stuff with matrices. For those of you who are in computer science, matrices are like arrays. For those of you who are not in computer science, matrices are just like a grid of numbers. But yeah, so like people will say it's about matrices, and it's not really. It uses matrices, but it's not about matrices in the same way that like computer science is not about coding, right? Like coding is a tool that you might use in computer science, but it's not computer science, right? Sure, you can find other examples like this. So yeah, what is linear algebra? It's a very hard thing to define. I'm not really going to define it for you. I'm hoping that through this course, you'll see that it takes many different facets, I guess, different avenues to, or different like pieces to it. But yeah, I guess we'll start talking about linear systems. So that's where the course starts. In high school, you should have learned how to solve a system maybe that looks like this. 2x plus y 6. If I gave you this system from like high school, show of hands, who knows how to solve that? Cool. Most people? Good. What would be the first step? Yeah. Yeah, high school. Go easier than that. Yeah.
Multiply the first equation by 2 and subtract it.
Yeah, I'm thinking of an even easier way. That is one way you could do it.
Addition.
Sorry?
Addition of equation. Removing the one variable.
Yeah, right. So like, let's say maybe we take this top equation, and what I'll do is I'll say x equals, I'll add y to both sides, right? So I get x equals 1 plus y. And then I can plug that x into here. So I can say, let me get 2 times 1 plus y plus 6. Plus y equals 6. And then I could expand this. I would get 2 plus 3y equals 6. So I get 3y equals 4. If I subtract 2 from both sides, y is 4/3. And then I could just figure out what x is, right? I could go, well, if we know that x minus y, is 1, then I can plug y in there, and I would go x minus 4/3 is 1. So x, if I add 4/3 to both sides, I think I get 7/3. So we have a solution, right? We found an x value and a y value that solves this system. Now, here's something I want you to realize is that we found one solution here, but it's possible that there's not, that the number of solutions is not 1. There's actually 3 possibilities. Does anyone know what they are? Yep. 0. So maybe I should start with 1, right? Say that you have 2 lines and we wanted to find, because we're talking linear algebra, so lines kind of make sense in a sense. Each of these are lines. And we're sort of trying to find like the POI between those lines. In terms of the number of POIs, we can either have 1, right, which is like just one spot, or we could have 0, which is like the 2 lines are parallel, right? They're never going to meet, yeah. And infinite, right? Infinite would be like if you have 1 line and then you have a second line that runs right on top of it. So then there's like infinitely many points where that intersects, right? Can I have 2? Why? Me neither, really. Because they're lines, right? Like you can't have a line that like loops around because it would have to bend, right? It can only intersect once, 0 times, or infinitely many times. So when we solve a system like this, the only options are that we get one solution, which we did here, or we get no solutions, or we get infinitely many solutions. That's it. Always those 3. So if you're ever doing a linear algebra problem and you get like 2 or 3 solutions, you're not doing it right because that's not possible. Yeah. No, not a question? Cool. Okay. So I'm going to introduce some terminology. We say that a system is consistent. Does anyone know what a consistent system is? Yeah.
So here's the key equation: x and y will equal, they'll both equal the same. Like x equals 1 was the first equation, and the second equation f equals 1 too.
You're sort of on the right track. Yeah.
The equations which have one or infinitely many solutions.
Yes, exactly. So it's basically these 2 cases. If it's one of those 2, then we call it consistent. If it's this, then we call it inconsistent. So if it has at least one solution, then we say it's consistent. Cool. But things can get difficult, right? Like with your previous knowledge, like prior to this course, solving something that like, maybe if I gave you x, y, z, and w as variables, and I gave you 4 equations, that would be hard to do, right? Like using like this kind of method, like how would you even start that, right? So we kind of want to introduce a systematic way to solve these kinds of systems. When is this important, you might ask? It's important for basically anything that has multiple dimensions. And like every kind of problem has multiple dimensions, right? Even if it's not like physical dimensions, if it's just different properties, like, I don't know, like temperature, time, space, right? Like all these different things are dimensions. So if you're doing any problem that incorporates like any different kind of measure, like more than 2 different kinds of measurement, then you're going to need linear algebra at some point. It's very useful. So let's say, okay, let's say that I give you this system. Copy it off my notes, so please forgive me if I'm looking down. So y minus 3z 1, 3x plus 6y minus 5z. Also, please stop me anytime if you're confused. I don't care, just shout. So say that I give you this system to solve. The first step that we do in linear algebra is we turn it into what's called an augmented matrix. So the idea here is that we want to convert it into this grid of numbers. Now, why? The reason why is because we have like x, y, and z here, but the problem wouldn't really change if I called these A, B, and C, right? Or if I called them like, I don't know, L, M, N, right? It doesn't really matter what I call them, right? So like, we can just get rid of them, right? We can simplify our problem by getting rid of them. Really, all we care about are the coefficients in front of those numbers, right? So we care about, in this case, 1, 1, 2, 2, 4, minus 3, 3, 6, minus 5. And we also care about these numbers on the right side of the equal sign, right? So 9, 1, and 0. This is almost what we call an augmented matrix. It's missing one thing, which is a little line that goes right there. Why does a line go there? Anyone know? Yeah? Yeah, it's basically just like an equal sign, right? Now here's the thing I want to try and get through to you. Sorry. This thing is probably going to, sorry, it was trying to kick me out of the call. So the one thing I want to try and get through to you here is that that line doesn't mean anything mathematically. All it is like a cue. It's like a reminder that there's supposed to be equal signs there. You put it in there for you, not for the math. It doesn't matter for the math. Okay, so we've put it into this augmented matrix. Now, sort of, I guess the question is, how do we solve it? So what I would do, what I'm going to introduce here is what we call elementary row operations. Elementary row operations. So elementary row operations are things that you can do to that system that doesn't change the final solution. So it doesn't change what answer you would get for X, Y, and Z. Does that make sense? Cool. So the first thing you can do is swap rows. Now, why is that? Say that I was looking at this. Maybe this is called line A, and let's call this line B. Would it make a difference if I asked you to find the point of intersection between line A and line B versus if I said find it between B and A? Doesn't matter, right? So that's all you're doing. When we say we can swap rows, we mean it's not going to change the solution. It doesn't matter what order I tell them to, right? The second thing is we can multiply or divide a row by a constant, and it can't be 0, because if it's 0, weird things happen. Say that I multiply line A here by like 2. Doesn't change the answer, right? If I make the line bigger, it's not going to change anything. So we can do that. Doesn't change the solution. Part 3. I can, and this one's maybe harder to see visually, but I can add a multiple of one row to another. So I can do like row 1 plus 2, row 2. I can also subtract because the multiple could be negative. Does that make sense? And it's hard to show with this. There's probably visual ways to do it. I just don't know how. Cool. So let's go on. Any questions before I move on? Okay. One quick piece of terminology. I want to introduce the term homogeneous system. Does anyone know what homogeneous means, or homogeneous? Yeah?
All equal to 0.
Exactly, right? So if I say like solve the homogeneous system, I just mean everything on the other side's equal to 0, right? The reason why that's special is because you already know one solution if it's homogeneous. You instantly know one. That solution, does anyone know what it is? Yeah?
There would be no solution.
There would be a solution.
There would be no solution.
There would be, I'm not sure what you're saying, sorry. There is a solution.
Yeah.
Yeah. All zeros, right? It would be 0, 0, 0. X equals 0, Y equals 0, Z equals 0. Because if all of this side was equal to 0, like let's look at this last equation as an example. If I do 0 for X, it's 3 times 0, plus 0 times 6, plus 0 times 5, right? So it's 0. So if you have a homogeneous system, 0 is always a solution. So there's no case where you can have no solutions. And maybe that's what you were trying to get at. You either have one or you have infinitely many. Yeah.
But I thought it like 6y minus 6z and y is
Well, then it should equal 0 on the other side, but that would be an extra solution, right? So if you had like 6y minus 6z equals 0.
and then like 4y minus 4z.
Yeah. Y and z could be anything, right? So if I put like 1 in for each of them, it would be like 6 minus 6 equals 0, 4 minus 4 equals 0. If I put in 2, it would work, right? You can put in any number, so there's infinitely many
So
solutions.
that costs more.
It's still homogeneous, yeah. It's homogeneous if you have zeros on the outside. That's the only condition. And it will never have zero solutions. It will always have at least one. In this case, it is infinite. Does that make sense? Cool. Good question. Okay, any other questions before I move on? All right. Let's try, maybe I'll introduce another quick terminology. I know there's a lot going on in this first tutorial, but hopefully you're with me. So there is a matrix form called row echelon form, or REF for short. It requires three things, and I'm going to sort of write them down. The first one is leading ones. So basically, as you go across the matrix, if you're looking at a row that is not zero, so if it's not just all zeros going across, the first thing that you encounter that's not a zero as you work across has to be a 1. If that's the case, then it meets the first step. Make sense? First thing you meet when it comes across has to be a 1. Number 2 is that any zero rows, so by zero rows, I just mean a row that's like all zeros going all the way across, must be at the bottom. So you just have to have all your zero rows lined up on the bottom, right? If there's like 2 zero rows, then they would both be on the bottom. Does that make sense? Cool. 3 is, let me double check. Oh yeah, I phrase this kind of weirdly, but leading ones form like a staircase. Meaning that like, you have like a matrix that's like, say that I'm looking at something like this. Maybe I'll change some of these numbers a little bit. Something like that. This is a 3x4 matrix. This has that form where it's like the ones are in like a staircase form because like they go down and across. This is the best way I know to explain it, is like a staircase. It sort of has to trickle down. An example of something that isn't would be like this. You can see like it doesn't like you can't have a staircase, right? It has to sort of like continuously trickle down. Does that make sense? Okay, so if it meets those things, then it's in REF. So that matrix here is in REF. There's one extra thing, like a more specific form of than row echelon form. It's called reduced row echelon form. So reduced row echelon form has to meet these three things already. So it has to already be in row echelon form, but it has an extra condition, which is that everything above and below leading ones has to be 0. So this is not in row echelon form or reduced row echelon form, right? Because there's something above this 1, for example, that leading one that is not a 0. If I replaced these 3 entries here with zeros, now it's in reduced row echelon form because everything above and below all of the leading ones is a 0. Does that make sense? Cool. Let's go through a quick example. Okay. So I'm going to erase some of this because I'm going to use much. Does anyone want to take a picture of this before I erase it? I'm really quick to erase, so I'm sorry. If I'm erasing something and you don't want me to erase it, you want to take a picture or something, just yell at me and I'll stop. Okay, so let's start with a matrix. So say that I gave you a system and you turned it into the matrix, this matrix here. So we'll do 3, 1, minus 1, 1, 1, minus 1, 1, 3, and 2, 1, 1, 0. Does that make sense? So like that. Good. So then I start with that matrix, and I want to try and figure out what the solution to that system is. It would have been like 3x plus y minus z equals 1, and so on. Okay. But I wanted to figure out what x, y, and z are. What I'm going to do is I'm going to use a process called Gaussian elimination. The way this process works is I can use elementary row operations, right? So we remember there are those 3 row operations that don't change the solution. I can use those row operations to get my problem down to either row echelon form or reduced row echelon form. And when I do that, I can almost like read off my solutions. It makes it super easy. So the first thing I'm going to do here is I'm going to swap rows 1 and row 2. So when you're doing a row operation, don't put an equal sign because the 2 matrices aren't equal. Their solutions are equal. They're not the same matrix. So use like an arrow. I usually use like a little curved arrow thing and write the row operation above. So I'm going to swap row 1 and row 2. So I'll get 1, minus 1, 1, 3, 3, 1, minus 1, 1, and 2, 1, 1, 0. Cool. So that got me a 1 in the first spot, right? Because remember, we want the first thing that we encounter to be a 1. Cool. Next step. I want everything below that 1 to be zeros, right? So what I'm going to do is I'm going to say row 2 gets row 2 minus 2 row 1. The reason I'm doing that is, 3 row 1. Wrong number. The reason I'm doing that is because I want to get rid of that 3, right? So if I do this minus 3 of whatever's above it, that's going to make this a 0. Does that make sense? So the first row stays unchanged. Second row, we got a 0 here. It's going to be 1. Might get the math wrong, so please double check me. 1 minus 3 times negative 1, so that's positive 4. Then it'll be negative 1 minus 3 times 1, so negative 4. And then 1 minus 3 times 3, so it should be 8. And then the last row stays unchanged. All good? Cool. Next step. Maybe I'll try and get rid of that 2 and make it a 0. I'm going to do almost the exact same thing. So now in row 3, doing row 3 minus 2 row 1. That'll get rid of that 2, right? So 1 minus 1, 1, 3, 0, 4, minus 8. Is it minus 8? Yeah, it's minus 8. And then I got 0, 3, 1, minus 6. I'll let you double check that. Cool. Next thing I'm going to do, I'm going to divide this middle row by 4, because that'll get me another 1, right? So let's try that. 1 minus 1, 1, 3. I should write down what I'm doing here. Row 2 gets row 2 divided by 4. So I get 0, 1, minus 1, minus 2, and then 0, 3, 1, minus 6. Make sense? Yep.
Should that be a minus 1 on the bottom row?
Here?
Yeah.
Yes, it should. Thank you. I made that mistake last lecture on my notes too, so good catch. Okay. Next step. Row 3, I'm going to do row 3 gets row 3 minus 3 row 1. Why am I doing that? Because I want everything below that 1 to be a 0, right? So I'm going to get rid of that 3. And what I should end up getting is, last row is going to be 0, 0, 2, 0. I'll let you double check that. And then the next step is going to be row 3 gets row 3 over 2. So I'm just going to divide that bottom row by 2. Yep.
Can you be R2 instead of R1?
Yep. Good catch. I did it, I just wrote the wrong thing. Good catch. So last step here, 1, minus 1, 1, 3, 0, 1, minus 1, minus 2, 0, 0, 1, 0. Now it's in REF, not RREF, not reduced, just in row echelon form. Because we've got that staircase, everything below the ones is 0, and we have the leading ones, there's no 0 rows. So it's all in REF. I have two options now to find my final answer. The first option is using what we would call Gaussian elimination, which is sort of the process that we've been doing. But in Gaussian elimination, you stop doing row operations once you get to REF. Then what we do is we say, well, if I look at this bottom row here, I can translate that back to saying z equals 0, right? Because this is like 1 times z equals 0, right? So we know z equals 0. That's one part of our solution. Next part, if I look at the second row, that row says y minus z equals -2. But z is 0, right? So really that just means y is -2, right? Last step, x minus y plus z equals 3. I can plug in my values here. I have z is 0, so we can just forget about it, right? Y is -2, so -2, so it should be x plus 2 equals 3. I can subtract 2 from both sides, and I'll get x equals 1. There's our solution. Does that make sense? Kind of weird, it just pops up. Yep.
For the first step, instead of swapping, can we factor out 1 minus?
Yeah, there's other ways to do it for sure.
How do you know which one?
Whichever one you feel best with. Yep, there's absolutely no, I sort of, I described row reducing kind of like solving a Sudoku puzzle, where like, it's like, there's a bunch of different strategies you can use. There's no real like specific answer that's like, you know, one way to do it. But like, as long as you get to the right final answer, there's a bunch of different ways you can get there. Does that make sense? Cool. Okay. Instead of this, we could use a second method called Gauss-Jordan elimination. In Gauss-Jordan, we don't stop here. We keep going, and we go to RREF. So that means we need zeros above as well as below. So I'll do that over here. The next step would be to do row 2 gets row 2 plus row 1, or sorry, plus row 3. So I'm adding these two rows together to get rid of that -1. And I should end up with this 0, 1, 0, -2, 0, 0, 1, 0. Like that. Next step I can do, maybe I want to get rid of that one up there. So I'll do row 1 gets row 1 minus row 3. That'll give me this. I want to double check that I get this right. Like that. Good with that? No? Sorry? Good? Okay, cool. Awesome. Last step. Anyone know what it is?
Online plus R2.
Yep. So I'm just going to add these two rows to get rid of that -1. This. Maybe we're look at that. There's our answer. Right there. Cool? All right. In case you don't see it, x equals 1, y equals -2, z equals 0. Cool. Okay. With that said, any questions? All good? Cool. I'm going to stop this recording.